Imagine picking up a simple rock from the ground. It feels heavy, solid, and ordinary. But what if I told you that this rock holds a secret far stranger and more beautiful than anything we see in our everyday world? What if I told you that inside this rock lies light itself, trapped and frozen over billions of years, carrying a story that stretches back to the very beginning of the universe? Today we are going to uncover the hidden truth behind matter, energy, and the astonishing reality that every object around us, including ourselves, is a cosmic masterpiece made of vibrating energy and ancient light. By the end of this journey, you won't see a rock, or even yourself, the same way again. Every atom has a story, every particle a history, and every piece of matter a connection to the birth of the cosmos. So stay with me, because what you are about to discover will challenge everything you thought you knew about reality, and reveal the incredible secret that a rock is, in essence, trapped light. The idea that matter is energy in disguise comes directly from Einstein's revolutionary equation E gemischt hangt mc2. This equation reveals that mass and energy are not separate entities, but two forms of the same underlying reality. The E stands for energy, m for mass, and c for the speed of light, squared, a number so enormous that even a tiny amount of mass corresponds to an immense amount of energy. This means that what we perceive as solid, heavy matter is actually condensed energy, compressed and stabilized into form. A rock, for example, appears fixed and unmoving, yet within it exists a tremendous reservoir of energy bound tightly together. When mass converts into energy, as seen in nuclear reactions, a small fraction of matter releases extraordinary power. This demonstrates that mass is essentially stored energy. The stability of matter does not contradict this idea. It simply means that the energy is locked into a balanced configuration by fundamental forces. Protons and neutrons inside atomic nuclei are held together by the strong nuclear force, while electrons are bound by electromagnetic attraction. These forces prevent the energy from dispersing, allowing matter to maintain structure. Understanding matter as energy reshapes our perception of reality. Solidity becomes a state of organized energy rather than an independent substance. Every object around us, mountains, oceans, buildings, and even our own bodies, is a dynamic concentration of energy patterns. What feels permanent is actually a stable arrangement of immense energetic potential, quietly existing beneath the surface of everyday experience. The statement that atoms are mostly empty space challenges our everyday intuition about solidity. When we look at a rock or a wall, it appears dense and impenetrable, yet at the atomic scale, matter is astonishingly sparse. An atom consists of a tiny nucleus at its center, made of protons and neutrons, surrounded by electrons that occupy regions of probability rather than fixed orbits. If the nucleus were the size of a marble, the nearest electrons would be hundreds of meters away, leaving vast emptiness in between. This means that nearly all the volume of an atom contains no solid material in the classical sense. Despite this emptiness, matter feels solid because of electromagnetic forces. When you press your hand against a rock, the electrons in your atoms repel the electrons in the rock's atoms due to their identical negative charge. This repulsion prevents the atoms from passing through one another. What you interpret as physical contact is actually the resistance created by these electric interactions. The sensation of hardness arises from the strength of these forces, not from tightly packed substance. Quantum mechanics deepens this understanding by showing that electrons behave like waves of probability, forming clouds rather than tiny spheres. Their positions are not precisely defined until measured, and their interactions are governed by energy exchanges. The structure of matter depends on these electromagnetic relationships, creating stability and form. Solidity, therefore, is not the presence of continuous material, but the result of invisible energy fields interacting in precise and balanced ways. The idea that light can create matter emerges from the principles of quantum physics and relativity, where energy and mass are deeply connected. Light is composed of particles called photons, which carry energy but have no rest mass. Under ordinary conditions, photons travel freely at the speed of light and do not form stable matter. However, when photons possess extremely high energy, such as in the intense environment shortly after the Big Bang or inside powerful particle accelerators, they can transform into matter through a process known as pair production. In pair production, a high-energy photon interacting with a strong electromagnetic field can convert into a particle and its corresponding antiparticle, typically an electron and a positron. This transformation obeys Einstein's equation E = mc2, where the photon's energy becomes the mass of the newly created particles. The process also preserves conservation laws, such as charge and momentum, which is why particles are produced in pairs with opposite properties. This demonstrates that mass is not a fundamental ingredient separate from light, but can emerge directly from energy under the right conditions. In the early universe, radiation dominated everything. As the universe expanded and cooled, energetic photons continuously converted into particles and antiparticles. Although many of these pairs annihilated back into light, a small imbalance allowed matter to survive. The atoms that later formed stars, planets, and rocks ultimately originated from these transformations of radiant energy. Light did not merely illuminate the universe, it participated in building its material structure through quantum processes governed by fundamental physical laws. The concept that quantum fields build reality arises from quantum field theory, which describes the universe not as a collection of tiny, solid particles, but as a network of fundamental fields extending throughout space and time. Every type of particle corresponds to its own field. There is an electron field, a quark field, a photon field, and others, all existing everywhere simultaneously. What we call a particle is not a separate object floating in space, but a localized excitation or vibration within its underlying field. In this framework, reality is more like an ocean of interacting fields than a set of miniature billiard balls. When energy disturbs a quantum field, it creates a ripple that behaves as a particle with measurable properties such as mass, charge, and spin. These properties arise from how the field vibrates and interacts with other fields. For example, electrons are excitations of the electron field, and photons are excitations of the electromagnetic field. The stability of matter depends on the consistent behavior of these field interactions, governed by precise mathematical laws. A rock, then, is not fundamentally a solid block, but a stable configuration of countless quantum field excitations arranged in a structured pattern. The protons and neutrons in its atoms are themselves composed of quarks, which are excitations of quark fields bound together by gluon fields. At the deepest level, what appears solid and permanent is a dynamic, organized pattern of vibrating energy fields woven together across space. The stability of a rock depends on a delicate balance of fundamental forces that confine energy into lasting structures. At the core of every atom lies the nucleus, composed of protons and neutrons. Protons carry positive electric charge and naturally repel one another through the electromagnetic force. Under normal circumstances, this repulsion would cause the nucleus to fly apart. However, the strong nuclear force acts at extremely short distances and is vastly more powerful than electromagnetic repulsion within that range. It binds protons and neutrons tightly together, overcoming their tendency to separate and locking significant amounts of energy into a compact region of space. Beyond the nucleus, electrons are held in place by electromagnetic attraction between their negative charge and the positive charge of the nucleus. This interaction creates stable atomic structures and determines chemical behavior. The arrangement of electrons around atoms allows them to bond with other atoms, forming molecules and extended crystal lattices. In rocks, atoms organize into repeating geometric patterns, stabilized by electromagnetic forces that create rigidity and hardness. Gravity also contributes, especially at larger scales, pulling together vast quantities of matter to form planets where rocks can exist under pressure and temperature conditions that maintain their structure. The combined action of these forces prevents the stored energy within matter from dispersing. Instead of radiating away, energy remains confined in stable configurations, allowing structures like rocks to persist over immense spans of time while maintaining their physical form through continuous force balance. The idea that the universe is frozen radiation refers to the transformation of primordial energy into the structured matter we observe today. In its earliest moments, the universe was an extremely hot, dense state dominated by radiation, high-energy photons moving freely in an expanding sea of energy. Temperatures were so intense that stable particles could not exist for long. Energy continuously converted into particle-antiparticle pairs and back again. Matter and radiation were in constant equilibrium, with light effectively shaping the contents of the cosmos. As the universe expanded, it cooled. This cooling allowed quarks to combine into protons and neutrons, and later for these, particles to form atomic nuclei in a process known as nucleosynthesis. After hundreds of thousands of years, temperatures dropped enough for electrons to bind with nuclei, forming neutral atoms. At this stage, radiation decoupled from matter and began travelling freely through space, leaving behind what we now detect as the cosmic microwave background. What had once been a blinding ocean of energy gradually condensed into stable structures. Over billions of years, gravity gathered these atoms into stars and galaxies. Inside stars, nuclear fusion forged heavier elements such as carbon, oxygen, silicon, and iron. When massive stars exploded, they scattered these elements into space, where they eventually coalesced into planets and solid materials like rock. The atoms in a rock today were once part of high-energy radiation in the early universe, meaning that solid matter is the cooled, structured remnant of an energetic cosmic beginning. As we step back and look at the journey we have taken, the idea becomes undeniable. A rock is not merely a lifeless object resting on the ground. It is condensed energy, structured by quantum fields, stabilized by fundamental forces, and born from the radiant fire of the early universe. What appears solid is mostly empty space. What feels permanent is a delicate balance of invisible interactions. What seems ordinary is, in truth, extraordinary. A rock is ancient light that has slowed down, cooled and taken form. And this realization changes everything, because the same laws that explain the rock explain you. The atoms in your body were forged in stars. The energy that moves your thoughts follows the same principles that bind nuclei and shape galaxies. You are not separate from the cosmos. You are an expression of it. Organized energy, conscious starlight, the universe reflecting upon itself. When you next hold a stone in your hand, do not see something dull or simple. See a story that began billions of years ago. See frozen radiation shaped by time. See trapped light. May this understanding inspire you to look deeper, question more boldly, and never accept the surface of things as the final truth. The universe is far more mysterious and magnificent than it first appears. Good luck on your journey of discovery. Keep exploring, keep wondering, and thank you for being part of this incredible adventure.